Okay, guys, we're starting second lecture, Mystery of Physics.
Recording? Yes.
Number 2. Recording, yes.
Okay.
Okay, let's just finish a little what I was said in the previous lecture. Just want to tell some small things. First of all, there's another phenomenon that's pretty good to know, which is called entanglement in quantum mechanics, and it's a very old phenomenon. Actually, it was first noticed by Einstein, and they wrote one article that was called Epr Paradox. EPR stands to Einstein, Podolsky, and Rosen. There are two other guys who worked with him. So this is called entanglement. Einstein's goal was actually to disprove quantum mechanics. He was one of the founding fathers of quantum mechanics, so he made a lot to create this theory. But he believed that the theory itself will be derived sometime in the future, will be derived from theory of relativity somehow. So he didn't like the foundations of quantum mechanics. So there's some scientific things. So they created this thing, this theoretical idea of Epr paradox, which actually sets that the particles of matter can communicate with each other with infinite speed, like they be in the different parts of universe, many like billions of light years one from another, and they can communicate, right? So they formulated then this, and everybody found that actually this thing really belongs to quantum mechanics. If quantum mechanics is correct, then there should be this thing. So this communication should exist. So for Einstein, it was like disprovement of the whole quantum mechanics. For most of the scientists, the other scientists, they thought that it's actually, yes, it's weird, but somehow we should coexist with this paradox. Okay, but only recently, maybe a few dozens of years, recently, not just yesterday, but a few dozens of years, people started. They come to a moment where they can actually made experiments to prove this paradox, and it was proven, actually, in short. So what actually was found? That if we have some, like for example, particle flying this way, right, like quantum, right, some quantum, and then it breaks into two. There are lots and lots of such things how it can be done. Like one photon splits into two photons. Like one particle, like neutron, actually it's not stable particle. Neutron is not stable particle, so it can make two particles, proton and electron, and they will be flying in different directions. And their paths can go further. Like for example, okay, some billion years, right? For example, billion light years. And then according to this thing, or according to entanglement, it's the same thing. Actually, it's the same thing. According to this, if you measure if you measure some features like energy and energy like of this, or usually what they measure spin, so-called spin. Spin is a quantum number. It's angular momentum. They are rotating. The particles and they are rotating. So, and like for example, it's rotating like this, right? In the regular quantum mechanics, spin, like all other quantum features, they are so-called unstable. Not unstable. They are uncertain. So you cannot know what exactly it is. Like the position of the particle, you cannot tell. Particle may be here and maybe another galaxy. Actually, quantum mechanics is very paradoxical. Everywhere there are paradoxes. But interesting enough that if you measure like spin of one particle here like this, so this spin should be totally opposite. Exactly opposite. If it's plus, this is minus. Like this. And other things. So this means that these particles are entangled in some way, quantum way. And by measuring this, you somehow manipulate this. So it's sort of a communication, right? So you can change this changes too. in normal quantum mechanics, this spin is as unpredictable as this one. So this is unpredictable, this is unpredictable too. So like if the other guys measure, one guy measure here, another guy measure here, they should have totally independent results. But it's not like this. And it was proven. The last proof was like they measured the distance like about 2,000 miles or something. The last experiments. So it was proven that yes, they correlate somehow. But at the same time was proven, I would not talk about this as a long and very complex talk. For some reason, you cannot still really communicate with this. They somehow connected, but you cannot use it for sending information. That's another weird thing, but I would not talk about this. Just to know that there is such phenomenon, proven entanglement.
Question.
Yeah, sure.
It was originally one particle, right?
Yeah, this is just particular experiment. There are also body experiments.
Yeah. I'm just wondering how you got one particle split up so that one piece of it is 2,000 miles away from the other piece.
They just moving. How they do it? They send it actually. Like for this 2000, they use two lines, like optical lines. They're using photons mostly, and they send one photon with the one optical to one position and another one, so they have a distance 2,000 miles. I think, if I'm not mistaken, they made the same thing, the same experiment with a satellite flying above the Earth too, so they can use entangle. I don't know, probably with laser or something, or maybe they send electrons. I'm not sure. But anyway, this is pretty well proven right now. Already, I think maybe at least dozens or maybe hundreds experiments on that already done. Very different situation, not like even like that. Like for example, we were talking about Bose BEC, Bose-Einstein condensate. Remember this helium, right? Those particles in helium, they are actually entangled too.
And must it be from the same? Must this split happen for this connection to exist?
No. Like again, like for in helium, right? There are no splits. You just lower the temperature to, remember this, like 4.2 Kelvin, right?
Yeah.
And they become linked together, entangled. So there are very different ways to come to entanglement. So much more
atoms of helium, right?
Yeah.
Okay.
So okay. So this is just for you to know, just example. Another thing, just to have it in mind, to good. Remember, we were talking about that actually the universe is just one electron, right, which is returning in time many times, right? Just to understand what is going on there, we have main equations of modern physics. One is EMC squared, right? And another is the quantum mechanics one, which says that the same energy, any energy of any particle or anything, stone, whatever, this goes to any energy and any mass, anything, whatever. This sofa, our building, the earth, everything goes like this. This the same thing. It's applied to anything. It says that somehow any energy is connected with some frequency of the wave. Remember I told about de Broglie wave? This aristocrat, the prince actually was a prince of Holy Roman Empire. Actually, interesting enough. That's why probably he managed to put it into his thesis, PhD thesis, the idea of that any energy can be applied to some frequency of unknown wave. And the same thing comes with momentum. Momentum is mv. This is momentum, physical momentum. Remember this?
Mass velocity.
Mass, yeah. It's hk, where k is actually 2p, p is p, number p, and lambda is this model key. So it's there's a length of this vector,
Mhm.
and lambda is the length of this wave. So de Broglie, he postulated this. Okay, so he postulated there is a certain wave somehow connected with any energy we have around, any energy. So, and what is wave, right? Wave, if you think about it, it is about oscillations. It's some circulation. Like if you have a wave in the ocean, right? Actually, what goes inside the wave, there is circulation of the parts of water in this direction.
Okay.
Wave is going this way. It's going this way. Here the same. Here actually the same. So it's sort of so this frequency is sort of circulation, and this circulation, according to further advancement in physics, which I am actually applying, right? This goes to that thing. So
And
the wave is that rotation. The wave in time. So these waves are waves in time.
And just in case it helps you, Franny, because I was recently doing this in astronomy and I was talking about it with Papa, is the higher the frequency, the smaller the wavelength.
I see. Okay.
Yeah.
So generally, the higher the frequency, the higher the energy, and the smaller the wavelength. So that's the
I
connection.
don't know what that first symbol is before the wave.
The P or the H?
The H.
Yeah, I wanted to ask about that as well. What is H?
That H. What
H is so-called constant, Planck constant. There's a guy, Planck, or K, I forgot. I think it's maybe like this, Planck. No, that probably Planck. So he entered this constant into physics with the same equation, by the way, but he didn't think about real particles. It was different stuff. I won't talk about it like this.
Okay.
So this guy was really brave, right? As a real prince of Holy Roman Empire. So he introduced some weirdest thing ever. He said that all the particles, like stones, Earth, galaxy, they have their frequencies and the wavelength. So this is wavelength. And this is called de Broglie wave or whatever. Okay? So what kind of wave is it? And actually it has a lot to do, at least to my understanding, a lot to do with this returning of the particle in time, right? So let's calculate this frequency, right? Frequency is from here, right? Is E divided by H. H is about 9 minus by the power minus 34 joule by second. Very small thing, very small. And C here, right, is 310
8 meters per second.
meters per second, right? So we have this, right, E. And E we taken from here, right?
Okay, you're substituting the value?
So yeah. So it's MC squared divided by H, right? So we have like for example 1 kilo, right? So 1 kilogram of mass. C squared will be 1016 and 10 will be like 1017, right? And divided by 10 minus 34, right? Just you to understand what kind of frequency is it, right? And we have this all divided, all these measurements they're okay. So it will have minus 34 goes here, come here, right? So it will be 17 plus 34. It's 51, right?
Plus?
Well, it flips.
Plus 17 minus 34.
Oh, it's minus 34.
It's minus
Okay.
34.
I missed that part. Okay.
Yeah, that's why you said it was so small.
It's 10 to the power of 31. You make it cycles or radians per second. So cycle per second. Sometimes they write just that. Second minus 1 per second.
Okay.
Or even something like this. Whatever you want. So what it means that a mass, like you have some mass, 1 kilo, right? 1 kilo of steel, for example. it's circling in time 10 to the 51, 10 and 51 zeros times per 1 second. This is like, I don't know, humongous, what is terrible number, you know, extremely big.
So is that why we can't see it?
That's why we can see it, yes. We cannot even measure it. It's like, it's unmeasurable, like, and would be unmeasurable like for many hundreds of years ahead. So it's a very high frequency, and we don't see it, and we see it like the stone goes like smooth, right? And the length, not that you believe me, you can calculate it, will be the same thing like something like this, but totally opposite, because it's you need divided. Where's he divided, right? So here will be divided by lambda, right? So lambda, the wavelength will be 10 minus 50 something meters. Minus 50 something meters. It's like it's smaller than anything you can even imagine. It's extremely small. It's unmeasurable. Just for you to understand. So if we're talking about that our electrons, like for example protons, which are about 10 to the power of 80 in the whole universe, like of electrons and the same of number of protons, and probably something about these neutrons. So each of them making 10 to the power 51 rotations per each second. It's returning to the past and back with that speed. So it's not like through the whole universe, right? It just... Okay?
So you keep saying into the past. I just want to double check.
Yeah.
Is this official science or is this your calculations?
It's partly official, partly mine. I would say that there is a theory. I told about this. The Einstein apprentice John Wheeler. Remember, he actually suggested that the electrons are the same, identical, because it's just one electron, right? Another guy, which is pretty well known and Nobel Prize winner, Robert Feynman, he created a theory about it's called one electron universe.
Mm-hmm.
So it is in physics, right? But it's not proven, right? But in my theory, it is one of the significant points of the theory, right? So it's the cornerstone. So they're trying to prove it. It's difficult to prove, but if you make it a cornerstone, that you're getting a little different view on physics that you have now, right? So that's what I'm developing. Okay. Okay. Now let's go. Now this is about like quantum mechanics, right? Just a little. Now we'll talk about what is called theory of relativity. That's another cornerstone of modern physics. The first cornerstone is quantum mechanics. That was the previous and the part of this lecture, right? And now we'll talk about theory of relativity. So relativity. So the whole word of relativity means that something is relative to something else, right? So it's about this. 300 BC, about 300 before Christ, right? There was a guy, whose name was Galileo Galilei.
Mm-hmm.
What?
Galileo Galilei.
300 before Christ?
300 before Christ, yes. You know, the Greek guy. And he suggested what is
sure
called...
you're talking about, because Galileo lived in the, 17th century or 18th century?
BC, before Christ.
Yes, I know. So Galileo...
I'm sorry. You're right. That's not 100 BC. Yes, you're totally right. I was thinking about another guy. I'm sorry, I was preparing for another lecture. So.
okay.
Yeah, okay. He lived in, I think, 17th century. Yes. That's okay. But so what he was thinking about mechanics, right? He lived before Newton.
Mm-hmm.
So if you think about mechanics, he made lots of famous experiments, blah blah blah, and everything. And he postulates the thing that is called relativity principle. It means that the state of things that are going around you are the same if you are in the state of rest, you're standing, or you're moving in some closed room in the straight and very undisturbed movement, like in the ship with no waves. You're going slowly, and you're making some experiments. And he says that physics all will be totally the same in this room. Nothing changes. Nothing changes. So, in like common thinking, you may think like this. So if something is moving, like a stone, is moving with the speed of v, right, some speed, and you are sitting on like some measuring device, like a ruler with a clock or whatever, some physical device, you're sitting here and you are moving with the same speed v. So for you, this will be in rest. So if you're talking from this point of view of this device which is moving, it will be a rest frame of reference. So it's like v equals 0 here.
Okay.
So this is like if you're in a car and your watch is also in the car with you, the watch isn't moving in relation to you,
Yeah.
but it is actually moving with you at the same
Yeah.
speed.
Yeah. So it's pretty easy to understand. It's like
Okay.
anybody can see it. If your car don't accelerate, right? If your
Right.
car is moving
Yeah,
very
steady,
smoothly,
steady.
you won't notice the difference, right?
Mhm.
So, and actually mathematicians usually say that the relative speed of stone and your system is frame of reference. It's called frame of reference. Some device that you use to measure, right? Something. So this relative speed actually is the v of the frame plus the v of the object, stone, right? And this is v of the frame. Okay. So in this case, if you look at this, the speed are going. Oh, how to put it? This happens when you're going like this. Reference frame and object. So they are added together. Of course, this make one step, this one step, two steps, right? The relative speed is that. In this case, it will be totally opposite. It will be like this, right? Because it's
Yeah,
not.
you're going with
Yeah,
each
Yeah,
other.
so will be.
Yeah.
Will be like this, right? So you can think of the whole system that if you move with the same direction and smoothly and with the same speed, everything will be the same.
Mhm.
And there are lots of terms there, like this straight moving and smoothly moving frame of reference. It's called inertial frame. Why inertial? Because if you really accelerate something, so you see the effects of inertia, right? So when you accelerate, you immediately
Yeah.
you feel that your body going back.
Yeah.
When you brake, you're going forward, right? And the interesting now, by the way, that if you think about it, like it's pretty interesting because in non-inertial frame, which you're braking or accelerating, right? This force comes from nowhere. Nobody actually pushes you. Actually, you just somehow there's not. You can remove your back of your seat, right? You still be pulled there.
Mhm.
So force looks from nowhere. That's why Galileo talked about these inertial frames. So this was relativity principle. Okay, it was. Oh, that's why I take 300 years, by the way, because I think like about 300, almost 300 years passed before Einstein criticized this principle.
Uh-huh.
That's why I got this 300 years, right? It happened in 1905 when totally unknown clerk of Patent Bureau in Bern published in the central and the most famous journal of physics at that time, published a 31-page of his work, right? With no citing, by the way, no citing to any other people around. Not even one citation was on this thing. But anyway, and this starts theory of relativity. So what he says, if you remember, I told already that actually it's not theory of relativity, it's more theory of absolute, because what Einstein postulated, that the speed of light never changes. Whatever you do, speed of light is still this 3 meters per second. If you, like according to the Galileo principle, it should be like what? Like frame of reference, like plus c, right?
Mm-hmm.
Should be plus.
Mm-hmm.
But Einstein said that it would be c.
Yeah.
It's like you're not moving at all. Even more, relative speed of light to light, like two photons going together, or like this, or whatever. Like, okay, c plus c, or c minus c, whatever. C minus c.
How about c to the power
Will
of
be
c?
still c.
Mm-hmm.
This comes from the formulas. I'm just writing this to make it a little look paradoxical, but it comes from the formulas. I will tell about this formulas a little, just right away. So when this was analyzed and checked, there were experiments made and everything, right? So experiments actually were made even before this work, but Einstein claimed that he never read about it. I don't know. Nobody knows. Did he read about it or not? Nobody knows. But the experiments were done like pretty much like maybe 10 years before, 20 years before this thing, which actually proved that the speed is not changing. And the formulas which we'll talk right now, they called Lorentz formulas. They were derived before this work by Lorentz, Hendrik Lorentz. But anyway, so what Einstein actually suggested, he said that, okay, we should have relativity. Relativity should be there. We should somehow keep this relativity, because relativity is needed to picture of objective universe. You know, that the universe should not really be dependent on our movement. Okay, we move somehow, but why physics should depend on it, right? Like our frame of reference is changing.
Mm-hmm.
It has nothing to do with the object itself. Objects should behave the same way, right? So that was the idea behind this theory of this principle of relativity, right? And Einstein believed in that very deeply, but he had to put his own way he thought about it, because he had to put into this principle of relativity the theory of electrodynamics, which was developed before. And it was great, it was proven and everything, but somehow light did not want to behave. Okay, that's the problem with the light, was the most problem with the light. And that's why when he postulated this absolutes of just speed of light, but all the rest was like normal, looks like normal, he had to come to an idea that both space and time should be changed. So if you move just a little, but straight inertial frame still you should move, both x and both time, they would be changed significantly. Not that significantly. It should be the mostly significant when you come to the speed of light, close to light. But before that too, they're changing anyway. We just maybe cannot record it when you move slowly, but it's still there. And then there was a guy who was called Minkowski, who suggested that the length, that space and time is actually one space-time. They say continuum, but it's one thing, space and time, which looks sometimes like space, sometimes like time. So this is the concept of space-time paradoxically together. And he suggested that thing, that the measure of distance in this space-time, you know, the measure of distance in the regular Euclidean space, like where x, y, and z, maybe you know, it's Pythagorean theorem, right? So this radius, right, this radius squared is x squared, y squared plus z squared. This is, and this guy probably lives 300 BC. That's what I remember. He I think like 300 BC. Pythagore, Pythagore, right?
Pythagoras.
Pythagoras?
In English, yeah.
I think it's Pythagore. Okay, whatever. So this is called I don't know, length, right? This is called length. And what there was another guy who worked on this, who added here, right? Another dimension t, right? And he, of course, if it's fourth dimension, should be added another term here, right? So how he do it? He did it like this. He said that it should be squared, not r, but t, and this is like this. C is just a...
Is C light?
C is the speed of light, yes. Minus x minus z. And this is called tau, is called interval. C is speed of light, t is interval, t is actually the so-called rest time. Rest time is time how it goes when you're at rest. So at your place, at your clock. So you're measuring time on your clock, this is your rest time, right? Something is moving somewhere, it's their time, t.
Okay.
So here it's rest time, there's t, right? So of course if you're at rest, there is no x or y or z because you are here, right here. And t is still running, tau is running. Your question or?
Actually no, never mind.
Okay. So this is the formula of Minkowski. The formula is called interval. So it's a length, actual length, but in the four-dimensional space. Okay. Okay, we for our purpose we will do this thing. We just remove y and z, just simple. Let's talk about the stone that moving just along x axis, right? Just x, no y, no z, right? So only in this direction, right? Stone is going.
Mm-hmm.
So what we have here? Okay.
So we're assuming y and z are both 0.
Yeah, practically.
Sorry?
Y and z are both 0. That's how.
Yeah.
we draw them?
Because we are moving right on the x at the zero level, right?
Okay.
Yeah, sure. So what we do? We divide by c squared first, right?
Mm-hmm.
That's squared too, and then make it so make a square root, right? So tau will be square root, right? We divide by c squared, should be and minus. Oh, sorry. You should. I'm a little too fast. You understand that, right? It's simple. Just divide it by c squared and make square root from this.
Okay.
And now what we do? We take t squared out of this out of the square root. So t squared, right?
Mm-hmm.
So it will be t
Yeah. It'll be t. 1 minus.
Yeah. Oh, here will be 1 minus x squared divided by t squared. X squared divided by t squared divided by c squared will be speed, where speed is x.
X over t.
Hold on.
Squared?
What happened to t squared? In the second
T square we get out of the bracket, right? So we should divide this by t squared and divide this by t squared.
Exactly.
X squared by t squared is v squared, and c squared was there already.
Hold on.
Yeah.
Aren't we dividing? In which case it would be at the bottom.
T is here. We take t out of the.
Yeah, but you have to take it out of both sides.
Yeah. From
So
here it's 1. from here is x squared divided by t squared and divided by c squared.
Okay.
That's all.
So where does v come from?
It's like it equates to that x over t squared.
Okay.
X divided by t, this is the speed, right? Definition of speed. This is speed.
X divided by t.
T squared. Wait.
So
Okay.
what happens to the c? Because if it's
Still there.
But if it was x divided by c, then you'd have to divide x divided by c divided by t.
Okay, I'll do it like this. T.
I'll back off. If you can follow the math, fine.
Well, this is one.
Yeah, and then x over t squared is v.
No, but you don't get to the point where it's x over t squared. It's still x over c over t. And they're all
No,
squared.
it's
Okay. Sorry guys. Okay, I was too fast. I'll do that. Okay. First divide by c squared. Everything, right? We have.
No, that part.
No,
I got.
wait. Okay, divide. We have t squared, right? Minus x squared divided by c squared. It's okay?
mm-hmm.
This understandable?
Sure.
Now we take out of the brackets t squared. T squared 1 minus x squared divided by t squared c squared.
Yes.
That's correct?
Yeah.
And x divided by t squared, this is v squared.
Oh, okay. So you went back a step. Okay.
Okay?
I got it.
And now we're taking the square root of all this, and we have t, like the time of in one frame of reference, right? If it is moving frame of reference, and this is rest frame of reference. 1 minus v squared divided by c squared. And you see, there's a famous formula actually. We see what's happening. Whatever t is here, if v is close to c squared, if v close to c, this one close to 1, and 1 minus 1 close to 0.
Yeah.
So this approaching 0. So t multiplied by 0 would be almost 0.
Mm.
If v equals c equals, this is the case of light. And it's a really physical case, because light is a physical thing. It carries energy, and light has a mass too, because mass is energy divided by c squared, and of course root, right? So if v equals c, like it happens with light, the rest time for photon will be 0 totally, whatever t is. It may be billions of years, this t, but multiplied by 0 will be totally 0. This is the main thing which we have to discuss. So you got this, right?
Mm-hmm.
So this comes from this interesting change by Einstein. Now the consequences of this, which even Einstein, interesting enough, he never discussed. Of course he understood it, but he never discussed because it was a little, too radical even for him. So what we have actually here, we have a Big Bang, right? And Einstein lived, he was in pretty well condition when the theory of Big Bang came and it was proven and everything, so he knew about this stuff, right? So there's a Big Bang. Big Bang is a big explosion, right, or something like this.
Yeah.
So the first of all, what was created there was light. Seems like that. There was light. The first thing we created light. And then it's come expanding, and expanding, universe expanding, it's like expanding, that's like a big bubble. Like a big bubble.
Dad, not.
What?
Anton.
That's fine.
Go ahead.
Big Bang, it's nowhere on this bubble, but we live on this bubble, on the surface of the bubble. It's four-dimensional bubble, 4D bubble. And this bubble is expanding everywhere, right?
Okay. So far, so good.
Just-
Yeah, I'm trying to picture time expanding.
it's not time expanding, time
If
is
it's
just...
a four-dimensional bubble, then the time
But
would
time
also
is
be
running.
expanding.
But time is running. It's expanding by definition. If we talk about time, time is something that runs. Unfortunately,
Maybe expanding is not the word.
no, it is the word. It is the word really, because the picture is like this.
Okay.
So it's like this bubble expanding. Just one of these dimensions is time, which runs by definition. That's all.
Mhm.
So it's you shouldn't speak about time. It's a good question, by the way, just to talk. So time is expanding by definition of time. That's all. And of course, it is included into this theory and expanding of the bubble. It is called, you may call it ruling parameter, right? T is rules everything. You change T by yourself to take a look what happens after 1 second, 2 seconds after Big Bang, like a million years after Big Bang, right? So you change the time. In nature, of course, time runs by itself. And all the others, X, Y, and Z, they are expanding this, according to this formula. This is the formula is connected with the universe, right? So all our galaxies are somewhere on the surface. Galaxies are created later, of course, but they are on the surface. First were like light photons. They were everywhere on this bubble. Here we say that they are going in the whole directions, but there are no point of Big Bang on this bubble actually. Point of Big Bang was here. And the bubble was, going. So Big Bang, if you want, it was everywhere. From our point of view, it was everywhere. And because the size of this bubble was expanding, right?
Mm-hmm.
All the waves become like, they call it diluted, but they actually pulled like a spring. You see the spring when you go it. So if in the beginning the light was like this, later it was become like this, and then like this.
Redshift.
So just yes, this is called red shift. Yes, red shift. And we know it exactly that it's happening because the further it's from us, like for example over here, right? The further you go on this surface, the more expansion, more this red shift is because of the wave until it goes, it expands.
Fun fact, they
Keep
call it
expanding.
redshift because yeah. So longer waves of light look more red to our eyes. Shorter waves look more blue.
Okay, I see.
So most distance objects are quasars. They are like active nucleus of galaxies. No galaxy any yet formed, just the nucleus. It's very active. It's like exploding all the time. And those quasars, they have a great red shift, so great actually that the whole thing, the Big Bang light that came to the Big Bang light is the light exactly from this explosion. It's not even quasars. We have this Big Bang light. We measured it. It was found in 50s. We can see it even in the old TV. If you old TV, remember, if you put it between channels, you have this so-called white noise.
Yeah.
There's something on the screen, right? About 10% of this white noise, actually it is the picture of this Big Bang explosion. So the light we can see by our TV. The redshift from Big Bang is so huge that it comes to the range of to the waves of TV waves. TV. So the light becomes electromagnetic wave of how many meter range. So we can see it is proven very well. So redshift, Big Bang, everything, right? But now we're coming to Einstein and this idea of photons with no time, right? Photons, this way or another way, they were emitted in the Big Bang explosion, right? And they go, like for example, to our time, as our time, right? Or current time. And they go somewhere in the future too, some distant future. Okay? To our time, this distance is about 13.5 according to experiment, actually, it's measurement, astronomical measurement, 13.5 billion years. Billion years of time. And 30.5 billion of light years in space. So, right. So the time is 13 billion years. For us, we are moving here. You see, we are expanding. Remember this formula, Lorentz formula, or Einstein formula, whatever. We have this time t. This is our time t. But for photon, his time is at rest. He's not moving to himself. If you sit on photon, you're not moving.
So from the photon from the Big Bang is not moving?
No, it is moving. But his time, it is photon
himself.
rest time, tau, equals to t, which is 13.5 billion years.
Yeah.
T here, right?
Yeah.
Square 1 minus V is C, V equals C, right? C squared by C squared, divided by C squared. This is 0, so tau rest time photon equals exactly 0, precise 0.
So the Big Bang is always occurring for a photon.
Yeah.
Not only always occurring, it also occurring in the distant future.
No, it's just, it's eternal.
And remember, tau, it's time, yes, it's time like physically, but it is actually the measure of distance in the 4 dimensions. It means that this point, and this point, Big Bang is everywhere here. It's still, yes, you're right, it's still going, but it's not going because the whole time of this photon is 0. It means that this time, this point and this point are 1 point. Just 1 for photon. The whole universe, the distance, right? Whole universe, 13 billion years for light years for us, and distant future for somebody. For photons, just almost 0. And not only 0, but this photon and this photon is one and the same photon. There's no change with him. He didn't change because for 0 time he could not change. It, right? Not he, it. So it could not change. So it's the same here. It's still photon of Big Bang here, and Big Bang is still going here and here. And now how many photons we have around? Much more than electrons. Like electrons are 10 to the power of 80. Photons much more than that. Photons are everywhere. You see, we use a light, right? And this microwave is called this Big Bang light. It is called microwave radiation, or fossil radiation sometimes. Fossil radiation because it's fossil from here. It's everywhere too, right? So what we have? We have interesting thing that universe actually, according to light, to light frame of reference, it actually totally, how it's called, collapsed, connected. So there's no distance between this point and this point and this point. There's 0 distance. Yeah, actually it comes not only for time. If you measure from his point of view, from photon's point of view, this distance, like x, right? X like in the rest, it's 0 too. The size collapse too. Yeah, according to the Lorentz transformations, which Einstein derived by himself too, but Lorentz did it before. But anyway, so according to modern physics, which is already here, 1905. Remember? So it's for already how many? 2019 minus 1905. How many years? 109, right? 110 already, right? So
114.
we have this physics already for 110 years.
Yeah.
And people, interesting enough, I read lots of articles and lots of books and manuals and whatever. Nobody mentioned this. Interesting enough. Nobody probably want to discuss this little too off for many people, starting in Einstein himself. Never talk about this, but it's obvious. It's obvious right from the formulas. You cannot argue with this in this theory. And where I would like to finish this thing, that remember this, there's only one particle which we call universe, right? There's one quantum which is universe, and which is what is doing? It's going in circles, right?
Mm.
And we can ask what speed is. Now we see how speed can affect the things, right? So what speed this particle or whatever how we call it, right? Proton. Sometimes they call proton, but it's the same for any particles. Electrons, protons, neutrons, they're all like this. In 2005, the guy called Penrose, what's his name? Roger Penrose. He's a famous mathematician and physicist. He found out that actually, if you put this picture, right, like CT, this is time, this is multiplied by C, just to make it simpler looking. So the speed of light will be like this.
Okay.
X divided by CT, right? This is V equals C. This picture, and this is opposite. V equals minus C. Time goes this way. This is X, this is minus X, right? So any particle which is moving slower than C, it goes somewhere here. This is resting particle. There are no X changed. It's not moving. Only T, only time, right? This is photon, right? Photon cannot be actually by himself, from our point of view, it cannot be at rest. It can be at rest with himself, but not to us. It's moving with the speed of light all the time. Remember, C is absolute. So photons are going this way or that way. But any other particles like that having mass, that's called rest mass, by the way, rest mass, M0, rest mass. Like electron, proton, or whatever, they can move with the speed 0. They can be at rest, right? Just like my pen, right? It's here. It's not moving anywhere unless I'm doing this. So what Roger Penrose found out from the main equations of quantum mechanics, it's called Dirac. It's Paul Dirac who first derived this equation, a Dirac equation for movement of any particle, any quantum particle. And Penrose found that actually the Dirac particle, or any particle that we have, it moves like this, with the speed of light, but like this. So the angle is always the same. It's V equals C, or V equals C, or V minus C. It goes like this. And that's why we see that it's like resting. But it's not resting. It's moving with the speed of light. It's going like this. Just like vibrating. We are coming to go. So you see this, right? So why it is so important? Because actually he proved, and it's proved, physicists not yet come to understanding what actually happened in this 2005. But what actually happened, he proved that all the particles, not only the light, but all the particles moves with the one speed, and the speed is C. The speed is the universal speed of everything. Everything moves with the speed of C. And it means that from their rest, in their rest frame, their time is not moving at all. Like for photon. For photon, time is not moving, right? It's zero. The same thing for any other particle. That's a very interesting thing, and it means that with this spiral of any, of any particle, time distance from here to here for the electron or proton or neutron or whatever other particles, the distance between them, their tau, their rest time, is equal zero. And it means that if you touch particle here, this particle can be very difficult, very distant from you in time and everything. It exactly resembles what you change here, something happens here immediately, because the tau is zero, it's the same particle. What I mean that these formulas they actually prove that electrons are the same, and if they're moving in this way, they are actually creating the whole spectrum of paradoxes of quantum mechanics. All these can be derived from only this idea, because there is one particle, it forms the whole universe, and the time is zero for this between any how you call, I don't know how you call this, clones, maybe, of this particle.
So is that why you started with the entanglement?
Remember? That's why I started from entanglement. Those, you see, these are different electrons. Yeah. Look like different, but they're not different. They're identical.
That's why,
and they are entangled. And the entanglement comes from this, because they're just one. The distance between them in space-time is zero, actually. But we see it opposite, in a very opposite way. We see it like zigzagging, and that's why we see distance, particles, and all that sort of thing, like in kaleidoscope. You have seen this kaleidoscope toy, right? So one or a couple of glass particles there, they create like a whole infinite of patterns, of colored patterns, and they're changing all the time. That's how universe looks like. It comes from one particle just explodes into everything. Thank you. Questions?
No questions for me.
You understand everything, right? Okay. No? Yes? Okay. So I would love to make another one a little later, another lecture on a little different things. But this is forms like the modern physics in its best, right? All the paradoxes that actually like boiling in modern physics, and you want to understand what kind of, from one side, it's extremely interesting thing and very paradoxical, right, and amazing and everything. And the other side, it has other consequences, right?
Consequences, yeah.
Other consequences that it goes from here too. But till the next one lecture.
Are there other people exploring this avenue?
Yes, there are many people exploring, not exactly that, right? But for example, Penrose, it's his thing, right?
Yeah.
Of course, they are thinking. They are really deeply thinking. Not lots, quite a few, not lots. But some few deep guys like Penrose, they're deeply thinking into it. Yes.
What would this help us achieve? I understand the concept. I understand. What's the overall goal? What would it help?
Oh, you mean to ask? Okay, this is question already not to the lecture, right? I'll finish the lecture. Thank you very much.
Okay.